Okay, just I'll introduce myself. No problem. Okay, so I'm going to talk about the lifting the degeneracy of a quantum spin liquid phase by uniaxial pressure. Okay, so I have constructed my talk is as follows. The first, I would like to give you a brief introduction, and then I'll talk about Miosa technique, and then about this system, and followed by some Miosa studies on uniaxial stress, and then conclusion and outlook. Okay, so I think some of you know me, and most of you probably do not know me. So therefore, I thought to give a little bit introduction to myself. And actually, who are we? I'm coming from Technical University of Dresden. So Dresden is basically located eastern part of Germany, and we are actually having a physics department. And in physics department, we do basically microscopic properties of. We try to understand the microscopic properties of correlated electron systems. Okay, so in particular, we do try to understand unconventional superconductivity and of course this unconventional magnetism. And in this frame, basically we do frustrated magnetism and altermagnetism. Okay, so in this session of this, basically we are having this frustrated magnetism. Okay, the parameter ranges we use magnetic field, uniaxial pressure, low temperature to tune the system. Okay, so essentially two experimental techniques we are using. One is nuclear magnetic resonance. So we have just recently developed a kind of NMR probe to study also for the CFMS compatible, and also we do basically the muon spin rotation experiments, and for that we need large scale facilities. So therefore we travel around. So this is my friend Hans-Henning Klaus, which is one of my irreplaceable comrades. So you see in the middle of the night he was doing MUSR experiment and trying to do something. So we work together. Okay, so this is the framework what we do, and of course some of you know that I also try to popular science. So I try to write Bengali books in Bengali for science books in particular. So I have written several books. So 2 is already there, and then one is coming up, which is Pratishambo this year. So if you are interested, please read it, and also encourage this to read to the students. And it's a popular book. So above 10th standard, everybody should able to understand these things. Okay, so these 2 slides I'll skip because Moik already gave an introduction to the frustration. So therefore I'll not talk about, but I will give you some definition about how we see basically the quantum spin liquid. Yeah, so if you really study, if you really make a research in kind of internet, what is the definition of quantum spin liquid, you will find plenty of words, plenty of buzzy words are coming. It's strongly correlated, it's disordered, it's elusive, it's quantum, it's fluctuating, it's topological, it's long range entangled, frustrated, many things you will find it. Yeah, so along all these things, and being a poor experimentalist, we have constructed some of the definition to understand it. Okay, so I formulated the definition of something like that. Still it is more theoretical. A quantum spin liquid is a spin state without any spontaneously broken symmetry. Second thing, a quantum spin liquid is a spin state with fractional excitation. This is already getting complicated now. Okay, and then a quantum spin liquid state is a realization of gauge theory with quantum spin. Okay, understanding gauge theory is difficult. How to rationalize experimentals is difficult. So my last statement about this correlator spin, quantum spin liquid, as an experimentalist, I see like that. It is a highly correlated spin state without static long range magnetic order. So that means this is where we have to pin down. Okay, so the question is that experimentally, how to identify? Is there any smoking gun experiments to rationalize the quantum spin liquid? And the answer is no, you cannot do it so easily. You need many experiments to really make a kind of framework. So what are the things? Like magnetization, you have to do definitely, because you want to see your CW parameter, right? And then of course you have to do the thermodynamics, that means heat capacity. And then you can do thermal conductivity, because these are the places you essentially see low energy things and low energy dynamics you will see. And then of course AC susceptibility, and then microscopic probe like muon spin rotation, and nuclear magnetic resonance. These two techniques, as Shushanto Dattagupta was asking, is actually the very low energy scales you can track, fraction of micro electron volt only. Now if you go a little bit higher energy, which is neutron scattering, of course there you can see the momentum space, right? So that means Q dependence you can measure there. So therefore all the excitations or other things you can track it by neutron scattering. So these are the things I think is very important, and combining all these things, then you can tell, okay, this is going to be a quantum spin liquid candidate. Only single measurement to justify is difficult. Okay, so this is basically the fluctuation rate. This is, if needed, we will talk. So I will give little bit introduction to the muon, because Moyun didn't give the basic introduction of the muon. I will give little bit. So you know, the functionality of muon is similar to a secret agent. Like what a secret agent usually does, you know, the James Bond usually go to a place, spy around the places and crack the information, track the information and leave the place without giving any kind of stress about him or her, right? That's how a spy works. Muon exactly works like this, because muon is a fundamental particle. It has a lifetime of 2.2 microseconds and then decays. And what it usually does, it's actually implant to the muon, it's a sample, and sits close to the electron if you are really using the positive muon, okay? And then senses what is happening around in particular the internal field and the fluctuations of the electrons, and then decays into positron. And that actually carries the information. So that means it is not perturbing, not disturbing anything to the system, but carrying the information to a detector. This is how muon works. So I think this is a very sensitive measurement, very sensitive measurements, and expensive also. So therefore one should do muon experiments when you really want to know a very tiny internal magnetic field presence, or what is the level of the fluctuations of your spins are doing. In that case, muon is very, very sensitive. Okay, so that means what information it can gives you, as Moik little bit informed, the magnetic volume fraction, yeah. So how much homogeneity in your sample this can provide. It can gives you the frequency, that means the order parameter, not direct but indirect effect of the order parameter you can get. And of course this damping, this is the inhomogeneity with the spins, things this can give. And it has a sensitivity of 0.1 millitesla, that means 1 Gauss it can track. This is quite sensitive. And of course the fluctuation time window is 10 to the power minus to 10 to the power 11 microseconds we call it, but yeah, so it depends on the which muon type of source you are using. Okay, so I think as far as quantum spin liquid is concerned, there are several systems has been targeted, and basically there are some of the detailed investigation has been done, like you have zinc copper Haber-Smithite. There are a lot of experiment has been done. That is an interesting compound, AC equals to half system. And then also we discovered in Dresden sodium ytterbium sulfate 2. This is also quite interesting, but it's a triangular lattice. And we saw also the pyrochlore, and also today Moik shows about this holonium based kind of metallic proximity to the quantum spin liquid state. But still, one of the important question is we are actually facing is that how to really tune your quantum spin liquid ground state, right? Because we want to have a very clean system. Yeah. Now, as soon as you want to tune the system, you put some kind of pressure, right? Like some kind of other material you put. As soon as you put these things, what will happen? It will basically increase the disorderness of the system. So therefore, we have to identify or find a way to tune the system very clean way. And to do that, what you can do basically the uniaxial straining, and this is what I'm going to tell. And last 5 years actually I have been trying, or me and Hansen Klaus has been trying to find a system where actually we can use this uniaxial straining, and this is rather challenging because the sample what you are getting, like Haber-Smithite or sodium ytterbium sulfate triangular lattice, all of them are very tiny single crystals, or it's oxide even, but it is a very fragile. As soon as you apply a tiny amount of strain, it breaks. Yeah, so therefore after 5 years of lot of tried, we are not successful, but then it came to us this lead copper tellurium 206. Okay, it is not very well studied like low dimensional quantum spin liquid, but it's rather close to the 3D quantum spin liquid candidate. Why? Because there are a lot of measurements it shows, like it has a competing interactions of, it is a hyper Kagome structure, not a suitable candidate in general for quantum spin liquid, but still it works. And it gives basically kind of no magnetic long range order down to at least 50 millikelvin, and the MEOSR shows enhancement of the spin lattice relaxation rate and the persistent spin dynamics, and also neutron scattering shows some kind of diffuse scattering. Not only that, this system shows, and it has a very beautiful single crystals are available, and this is where actually we are headed, because finding a good single crystal is important for the experimentalist experiments we do. And it has many other degrees of freedom. It has a kind of some kind of specific anomaly which is 1K, and which is related to the ferroelectric transition, and it has a long strong thermal coupling, and also it has a strain sensitive quantum criticality. So a lot of competing energy scales in this system we have. So therefore it was a very suitable candidate for us to tune and to play around, and we did it. Okay, so it took some time, but it worked. Only last year finally we got some things. So how we did it? So you see, this is basically the hyper Kagome structures, and this 110 plane is essentially the interesting plane to apply the uniaxial strain. The idea is very simple, but to make it work, it's very complicated. What you wanted to do? Okay, I have a 1110 plane, and now I want to make a strain along this 110 direction. So what will happen then? Basically, you will change all the exchange energies things, because you are changing the lattice parameters, right? So that means you try to break some kind of symmetry, and that will influence all the properties what you are going to measure. And that's the simple idea. Usually it works with the, for example, hexagonal lattice, because you break the symmetry or A to B, like these things work. So this is what we wanted to do, and we did it. And what we have found basically, okay, these experiments I'm not going to discuss it, because it's a lot of experimental challenges, a lot of engineers, many people who are involved. If you are interested how it works in particular for a larger sample like 5 millimeter sample, we can discuss it later. Okay, let's come to the data, what you have found, and then basically from the data what information what you have found we'll try to tell you now. Okay, so this is the plot. In this A plot, number A, left panel A shows a zero field MEOSR under 1 uniaxial compression or stress in 110 direction. Okay, and this is the zero field spectra. Is the time axis, and this is basically the y-axis, which is actually your polarization or the asymmetry. What you see, we have applied pressure up to 37.7 megapascal, and starting from this ambient pressure. So this is actually the ambient pressure data. Okay, this is the magenta field circle is your ambient pressure data. As you increase the pressure, you see the relaxation start to increase a lot. So that means there is a very fast damping happening. Okay, this is at 0.7 Kelvin temperature. Okay, unfortunately we cannot go to 20 or 30 millikelvin, because it is experimentally so far is very challenging, because if you really go to such a low temperature, then there is a huge amount of heat load is actually jeopardizing our experiment. And now this is at 10 Kelvin, which is far above basically your any kind of ground state. So, and there you see this is our again zero, this is ambient condition, and this is our 1.4 megapascal, and this is 12.8 and 37.7 megapascal. Now it's the time to, from this data, now the time has come to extract information. Of course, if you from the data, if you want to extract the information, what you have to do? Okay, we need to take the help of theory, or we have to make a model, right? This is how you do in physics in general, because information is the thing what you want to produce to the others. So we do that, basically we make an exponential fit, a double exponential fit, but equation is not important here. Okay, so these are the best described data you can get by this model. This I am not going to talk, but if you are interested we can talk later. What you have found, let's put the outcome. So the outcome we have found, there are two relaxation channel is actually happening to this system. And now if you really make a model and a fit, then you get an lambda, but also Moik showed the extraction of your lambda values. Now you see, this is my ambient pressure data, which is actually below 1 Kelvin. You have a constant relaxation value, which is actually your persistent spin dynamics kind of things. That is the one signature, not the classical signature, but one signature of quantum spin liquid state. You have the fluctuating ground state, or no static ordering. Now, as you increase the pressure, what you see, your lambda first is dramatically increased and going to at least 10 to the power 2 higher values. That means you have a very fast dynamics, very fast decay of your muon relaxation. And how is it possible? And this is only possible when your system possesses a kind of a high degree of static correlation. Okay? We cannot tell this is completely static order, then you would have probably an oscillation or something like that. This is a high degree of static correlation. And the second part, we also need a slow dynamics. Yeah, we also need a kind of slow component to feed the things. And there you see that, okay, at ambient condition, more or less, our relaxation rate increases and then basically get a constant. Okay, so the take home message is very simple, that by applying uniaxial strain or uniaxial pressure, we definitely influencing our system in our relaxation channel dramatically. Okay, now the question is that where from these things are actually coming? And my systems are really homogeneous, or there is something happening to my crystalline symmetry, and that also you can do by the same measurements. So what you have to do for that, this is a simple measurements. So what you do when you are doing these measurements, you basically apply the pressure to your system. How do you do? You have a 4 piezo's, you applied an external voltage, okay, and that voltage basically make a displacement to your system, right, to your sample. And now this is basically my displacement, which is the microvolt, and this is my force, which is also microvolt. And if you make a plot, now you see, as you actually increase my kind of as the displacement changes through the force, which is applying the voltage, there is a linearity. But as soon as we go to 10 to the power 8 megapascal or near about by this pressure, you have a slope change, and that slope change doesn't recover it. What does it mean? That means I am actually changing my pressure, or I'm one particular direction, the other direction, and I'm slowly actually increasing the displacement values, and now suddenly there is a change of my displacement, and that is only possible if you have a crystalline symmetry is changing on the system. Yeah. So of course you may ask, what is the microscopic proof? Okay, we do not have, because it's a bulk measurements. For that we need to do X-ray scattering in under pressure. Okay, so now basically we can make some kind of small phase diagram. So these things have not been published, or these things has not been reported yet. So the thing is that as a function of strain or as a function of pressure, we can make a kind of small plot like that, which is one is basically lambda first. Now you see, these are the 0.7 Kelvin is actually kind of yellow, and then red is basically for 10 Kelvin, which is the lambda first. You see, these things is actually changing as you really go above 10 point some megapascal pressure. Yeah, so that tells you that indeed in my system, as I applying this one directional 110 directional pressure, I am actually modifying my system not only crystallographically but also the correlation point of view. I'm also modifying the system. Chairman, how much time do I have?
I think you have 5 minutes overall.
Overall 5 minutes. I'm talking time. Okay, so that means that so these are the first signature we got. Of course you can go a little bit more detailed experimental studies, and that detailed experimental studies, for example, we have done also the transverse field MUSR under again 110 uniaxial compression, and that is a clear cut. You see, as an experimentalist, as observable, you immediately see the dramatic change here, right? What do you see? This is the rate curve, which is the ambient pressure data at 0.5 Tesla. So we apply an external field, and then if you really apply the external field, what will happen? As Moik told, then muon has a gyro-magnetic ratio of 135 megahertz per Tesla. Okay, So that means as soon as it will sense a 0.5 Tesla field, muon will start to precess. Okay, as soon as muon will start to precess, what will happen? It will have a kind of frequency of oscillation, resonance. Okay, and that is basically the 0.5 Tesla, and you see a damping because of your, if doesn't really have any correlation, it will not damp out. If it doesn't really have any other static correlation presence, it will not damp out. It will be some kind of continuous oscillation you will find with a certain time scale, right? Now, as soon as you go to 0.7 Kelvin, okay, or this whole measurement is 0.7 Kelvin and 37 megapascal, what do you see? This is my data. So we have a large amount of damping. The oscillation frequency is the same. Yeah, the resonance frequency is same. So that means the magnitude of the internal field values or the external field values is same, but my damping is stronger. So that essentially tells you, okay, I have basically kind of very large or static correlation is developing as you apply the pressure. I think this already brings us to an kind of solid foundation that, of course, now lead copper tellurium to kind of system we can tune. Of course, we need more pressure maybe to really tune it, or need different kinds of samples or maybe other directions of the pressure to really see which directions actually we are moving. I think we are make much more detailed studies on these things. I think this I will not talk much. I'll just because of the sake of the time. So what the information now you get, lot of data, but what information you get, the take home messages. Yeah. So the message is very clear. The first, basically, I think we have this largely unaffected fluctuation rate because of the slow fluctuation, but our local field distribution, which is coming of your electron spins there, it's actually progressively broader. So that means the static correlations or quasi-static correlations are developing, but we cannot tell conclusive evidence of long-range ordering. If there would have been a long-range ordering, then you would have seen at zero field a well-defined static, well-defined order or well-defined oscillation or strong damping. That is not there, so therefore this we cannot tell. And now, of course, as I told you, you have an enhanced quasi-static magnetic correlations, and then we have a structurally disordered state now, but we need a further kind of more experimental investigation, in particular X-rays under uniaxial pressure to really see what is happening. And this system essentially now shows that, okay, I have a strong coupling of my lattice and the spin degrees of freedom for sure, and allows us to do this kind of MEOSA studies or this kind of studies in other directions. Now also we are definitely hopeful that we will get a kind of solid single crystals which is sustained with this kind of pressure, and we can essentially tune from completely disordered ground state to the ordered ground state. That means we need not to doping the things, you need not to introduce additional disorder which is jeopardizing our inherent physics. We can basically probe it by uniaxial strengthenings. Of course, now our next target is to do the NMR experiments on this system in uniaxial pressure. So I think there are many people involved in general because it's a big project. We do a lot of kind of Max Planck Institute, TU Dresden and PSI, we three basically developed this uniaxial strain, which is basically our one of the important thing for us. But whole work, what you see, me and Henning conceptualized, but I think he did a lot of analysis. Shohel, he did a lot of analysis of this data, and we look forward to a kind of good output from it. Thank you very much for your attention.
Quick questions. Yeah.
Okay. So I think the one thing. So okay. So just one thing. So if you showed this lambda versus temperature. So I was just wondering that the lambda gets saturated exactly at the same temperature where you have this ferroelectric transition.
Yeah.
So, I mean.
So I think that it is not that you have not thought about it. So we thought about it that I think still we cannot segregate or disentangle. This is really coming because of the ferroelectric degrees of freedom, and that actually making this kind of persistent or the continuous degrees of the fluctuation. But The issue is that, as I have already mentioned in the last slide of my talk, we have we believe on the basis of the experimental data that we have a strong coupling of the lattice and the spin degrees of freedom. If there is strong coupling of the lattice and the spin degrees of freedom, then muon essentially would see it, right? Because muon do not see the probe, muon do not probe the lattice, but it does probe basically the spins. So if it is a strong coupling, then it is very hard to avoid. This is what we see for the time being. It may change, the idea may change, yeah. It may change, but for the time being, this is our consensus. This is what we believe. Yeah.
We can get 2 more questions at most. We're sort of slightly out of time.
Thank you, sir, for the nice talk. So, for applying pressure, do you use diamond anvil cell for a uniaxial pressure?
No. I think I do not. Where from the question? Oh, okay. So I actually no. I think this is little bit different. Actually, the problem of the diamond anvil seal basically to make an uniaxial pressure is rather challenging. Yeah, of course you can go very high pressure, but uniaxial pressure, if you really have to do, for example, for this configuration, you see, this is my for example sample, right?
Right.
This is my sample, and this is actually somehow you place the sample here. Now, for example, this is one direction 110 plane. Okay. We're applying it. Now, here basically are some kind of piezos. Okay, you need a kind of piezo stacks, but here the problem challenges are here because you have a 5 millimeters of sample length or 6 millimeter sample length and 4 millimeter width and 0.5 millimeter of thickness. So imagine you need a 1000 Newton, to apply it, and this is very difficult. So therefore you need a kind of big configuration, kind of 4 large piezos, and then if 4 stacks, you can actually change the voltages and then play around with these things. So of course, if you have a tiny sample, right, like you for thermal conductivity or like AC susceptibility or magnetization, then you need 1 millimeter sample. Then you can, it's easy. Then you need a very small piezos. So only 20 volt or 30 volt or maximum 50 volt is enough to do it. But here you need 250 to 300, or if you really 2 stacks, you need 600 volt. Which is very, very thing. So therefore, diamond cell will not work. Sorry.
I think we should stop here because we're a bit out of time. Thank you again.
Okay.